All right, folks, so today we're just going to look at new ways to represent our vectors. We'll be performing the old operations on these new representations. Now, if we remember, a vector OP goes from the origin point O to point P if it is written like so. Now, if that's the case, okay, so we have a y-axis, we have an x-axis, we have a point, I don't know, let's say it's right here. We can call this point P. Then our vector has its tail at the origin and its head at point P. And that gives the x-coordinate of point P right here, the y-coordinate of point P right there. So there's my y-coordinate, and here is my x-coordinate. Fantastic. Now, we can break this vector down a little bit into its components. Now, you will have, for those of you who have taken grade 12 physics courses, you will have some experience breaking a vector down into its components. Now, where we're working right here, we're going to take advantage of a couple of unit vectors. This notation still is likely new for you. Now, these two unit vectors, vectors I and j, each have length 1, and that's how we know they're unit vectors, right? Every single unit vector has the length 1 unit. Now, in terms of vector I reaches 1 unit into the x direction. That is, vector I might look something like this. Vector j reaches 1 unit into the y direction. So vector j might look something like that. So we'll break it down like so. You'll sort of see what we mean as we talk about it, but really it means if OP is equal to AB, then our x-coordinate A here can be multiplied by, and really so our x-coordinate A, remember that's a scalar quantity, an x-coordinate, A can be multiplied by I, which is a vector, plus our y-coordinate B can be multiplied by our y vector, our y unit vector, j. So we'd be working with AI plus bj. Now what we're really doing there is we're adding. So let's say we have a point, we'll use this diagram once more way up here. What we're doing is we're taking a look and we're saying, okay, so this x-coordinate is the number of units that our point P has been translated in a horizontal direction from the origin. So what we're really doing here is we're saying, okay, so a vector like this would go to a point here, which would be given by an x-coordinate of still the same x as above, and the y-coordinate of 0. And then what we're doing is we're saying, okay, so that's great. Now our y-coordinate, or our y vector, might be broken down like this, where its x-coordinate is 0 and its y-coordinate is the same y value as point P. So what we're doing when we're breaking it down into components is we're saying, okay, so this vector given from the origin to point B, P, is going to be the same as the sum of vectors, the horizontal component plus the vertical component, like so. So you should see it in action right here. All right, so let's say we're working here. We have the point 5, negative 11. And our vector goes from the origin to the point 5, something like this, to negative 11. All right, so our vector goes something like this. Now, if we're going to write this in terms of its unit vectors, then we need to determine, okay, how many unit vectors are going to come across our x-axis from the origin to the same y-coordinate as our point P. There's point P down there. And we can see, okay, since my x-coordinate here is 5, then I'm going to need to use 5 unit vectors right here, something like this, 2, 3, 4, 5 unit vectors to get to that point. So I'm working here, OP is going to be equal to 5 times the unit vector, whoops, I won't use a hat there, I'll use a harpoon, 5 times the unit vector I. Fantastic. And then I'm going to ask myself, okay, well, how many vertical unit vectors will be needed right here? Well, I'll need 1, 2, 3, I'll need 11. How do I know 11? Because I know I'm going down 11 units. But then I ask myself, okay, so if I just add 11 vertical unit vectors, then that's actually not going to take me where I need to go, because then I'll end up somewhere right here. So I need to make sure what I'm really doing is I'm adding the opposite of 11 vertical unit vectors. I'm adding negative unit vectors. I'm subtracting these unit vectors because I'm going in a downward direction. So nice and easy. There we have just broken this up. We can write this in one more condensed way, and I'm sure we'll feel comfortable with this, which equals 5 times I plus, or rather minus 11j. Fantastic. We broke this down into its components nice and easy. Now every single possible vector in R2, which is in 2 space, which is using an x and a y axes. Every single possible vector can be broken down into I and j, because every single vector could be written with its tail at the origin. Every single vector, we're used to already writing points in terms of an x-coordinate and a y-coordinate. Now we're just doing so using unit vectors 5 and -11. You'll see, obviously, the same values came up here, the 5 and the -11. Those were the same values that we saw when we were just working with our coordinates from the get-go. Fantastic. All right, so we're going to work down here. We're going to have 4 unit vectors. We'll sketch all of them. Our first unit vector is given by OP, and it's to the point 1, 3. Okay, so whoops, rather our origin, we know where the origin is. There's no need to sketch it in there. We can go to the point 1, 3. Our point P is given here, 1, 3. Fantastic. So our vector is given from the origin to point P. Nice and easy. So you should be able to plot the remaining points here, OQ, OR, and OS. You should be able to plot the points and the vectors. Try it out here, and I'll say pause the video, try it out, and then come back and compare your work. Fantastic. So here you have it. We have our 4 vectors, P, Q, R, and S. Now notice, the question asks us to sketch the 4 vectors. If you forgot to sketch your arrows, if you had just sketched the points P, Q, R, and S, you would not have earned the marks here because you're not sketching the vectors. We've just sketched the points. The vectors are the arrows. They are from the origin to those points. Good. So now we've sketched those vectors. Now let's look at writing each vector in terms of their components. So we'll start off with vector OP. Now vector OP is given right here. We've seen it. It's given by the coordinates 1, 3. Now, if we're writing in terms of our components, we need to ask ourselves, okay, how many times do we need to use the unit vector I in order to get to this x-coordinate? Well, the x-coordinate is 1, so we're only going to the right 1 unit. So we're working here, and we're working with 1I plus how many j's? Well, our y-coordinate is 3, so we need 3 j's here. So plus 3 times j. And if we'd like, we can simplify that a little bit further. That's I plus 3j. Well done, nice and easy. Now I'll ask you once more. I'll say pause the video here. Try out OQ, OR, and OS. And then unpause the video and check your work. Good, so we see here just some keys. The vector OR, it doesn't have any y component. And that is really its y component is 0 because its y coordinate is 0. So when we're working with OR, we don't need j's in here whatsoever. The only unit vector we're relying on is unit vector I. Fantastic. Okay, so now let's take a look, and we're going to work with some vector addition. We're going to add vector OP plus vector OQ. Well, that's fantastic. So if I'm working over here, I can visualize this. I can take vector OQ, and I can add this to OP. I'm looking at something like that, and I need to try and figure out the vector that brings me from the origin way up here. Fantastic. So that's what it visually looks like. And I could kind of play around with that, and I could use that information, and I could say, okay, well, what I'm doing is there we are. What I'm doing is I'm working here, and I'm saying, okay, so my x-coordinate, let's see here. I started at the origin 0, 0, and then I moved to the point P, and that's 1, 3. And then I'm adding vector OQ, which is -1, 2. So really what I'm doing is my x-coordinate was 1, and it needs to have 1 subtracted from it, the one coordinate here, and really that's -1 added to it. And then my 3 vector needs 2 added to it. That's the y coordinate of OQ. So I'm working with 3 plus 2. Really, I'm working here, and I'm expecting to end up with 0, 5. And does that line up about with our sketch? Yes, it does. So fantastic. That's all well and great, but you might be able to recognize this is not really showing our work very well. We're not communicating what we're doing. So let's play around. Let's look at this nice and carefully. Well, what we're working with right here, we're working with OP plus OQ. Now, OP and OQ, we have broken down into their components. So let's use that information. Let's use our understanding of their components, what we did in section B. OP, I know, is I plus 3j. So that's I plus 3j. Fantastic. And then I can add here, okay, plus I'm working with OQ. Well, OQ, I'm working here with -I plus 2j. Fantastic. Now, if I add these together, this is what I'm doing. Then I'm working here. Okay, so I have I minus I. That one's, the second one came from way over here. Fantastic. Plus 3j plus 2j. Fantastic. So I'm working with 0i plus 5j. Is that what I was expecting? Absolutely. We've come up with the exact same answer, just with a more formal approach. Fantastic work. All right, now let's get a little bit more forward here. Let's sketch a few vectors from their components. All right, so I'm working here. I have OA. All right, I'm going to go here. OA will work in red. So from the origin, and I'm working with 2 times our horizontal unit vector I. So I'm working with vector I plus vector I. So that goes to my x coordinate 2 plus 1 of my unit vector j's. I'm working right here. The coordinates I can see here I'm working with are 2, 1. Fantastic, nice and easy. All right, so let's work with OB. And from here, okay, so I'm working with unit vector I once more. I'll go underneath this time. Unit vector I minus 3j. Okay, so I need to go 1, 2, 3. So I'm working right here. My point is at coordinates 1, -3. So my vector, remember, my vector here can be given from my origin to that point. My vector OA, if I sketch that one in its position from the origin to point A. Fantastic. Now let's sketch OC as well. We're working with -I. Okay, so I need to go 1 horizontal unit vector in the negative direction minus 2j. All right, so down 1, down 2. I'm working right here. My coordinates, -1, 2. Fantastic, folks. So if I'm writing these vectors in terms of their coordinates, oh, lo and behold, we actually already did that. Right, so our vector OA, and we should be following the same convection as we are in the notes and as they do in the text. OA is equal to, we need that equal sign here, is equal to 2, 1. That shows that we're working with a vector here. Fantastic. All right, if that's the case, vector OB, don't forget your convention here. OB is equal to the coordinates 1, -3. And what we're indicating with this notation is that our vector goes from the origin to point B, and that is to point 1, -3. Nice and easy, nice and fantastic. So OC we're working with here is equal to -1. Oops, should it be -2 over there? I apologize. There we go. Fantastic. Now, using these coordinates, okay, so let's play around. We're working with OA plus OB. That's what they're asking us for down here in part C. All right, so OA, we've already done something like this. OB, what we're working with right here, if we're adding it, then we're working with something like this. Now, if we're working with our coordinates, it can really help to have this sketched in, right? So if I put this back, and I'll come up with that on my own. What I'm working with here, okay, if I'm adding OB, then that's like I'm adding all of these blue vectors to the ending point of vector OA. So I'm working here, okay, so I'm going to add 1 horizontal vector. Fantastic. And I'm going to add 3 negative vertical vectors. So 1, 2, 3. So if I'm working to add these two vectors together, then I should be working from the origin, to this point here. I'm using my thumb pad, and perhaps that was a poor idea. And again, I can see, if I want to, I can see what I was using there. Let's pull that out. There we go. Yes, my logic adds up. I end up at the same location right here. So I need to ask myself, okay, what is that location right here? Well, I started off at the origin, so I started off at 0, 0. And I'm just kind of, again, this is informal, showing the work down here. The work is really being shown up there. So I go from 0, 0 to point A. Now point A is, I'll label it up right above, is 2, 1. Fantastic. So what I've just done there is I've worked with the vector OA. And then where I've worked from here, okay, so I've added, plus I've added vector 1, negative 3. Which I'm seeing my label got moved at some point. So let's put that in place. Oh my goodness, lots of things, lots of pieces have been moved in here. That's okay, I'll move them around and correct their positioning when I upload this to the classroom. I apologize. Fantastic. So, okay, so I'm working with 2, 1 plus 1, negative 3. What I can do is I can add their components. So I'm working here. Okay, so I'm working with 2 plus 1. Fantastic. I'm working with x coordinate 3, and then 1 plus negative 3 right here. Okay, so I'm working with 3, negative 2. Is that where I'm expecting to end up? Absolutely, because if I look at all of my unit vectors that are horizontal up here, and I'm working here, okay, so I have 1 horizontal unit vector, 2 horizontal unit vectors, 3 horizontal unit vectors. Fantastic. And then I look at all my vertical unit vectors, okay, 1 up, 1, 2, 3 down. I'm working with a net value of negative 2 vertical unit vectors. I get to the point 3, negative 2. Fantastic work, folks. Now, I think we have a bit more to go over. All right, so if I'm working with 3 times vector OC, here I'm working with some scalar multiplication. Whoops, and vector OC was green. So vector OC, I know I was working with the coordinates -1, -2. -1, -2, that's vector OC. Okay, if that's the case, then I could multiply both sides by 3. So 3 times vector OC is going to be equal to 3 times -1, -2. And what I'm doing is I'm distributing into the coordinates here. And that might seem a little bit odd, but it allows us to work here. It allows us to work with, okay, so I'm working with -3, -6. So if I'm working with a scalar multiple of a vector in coordinate form, I can multiply that scalar multiple in. So our generalized rule right here, all right, I'm working with k times vector v. I'll slide that down. If vector v is equal to ab, then kv is going to be equal to k times a, k times b. Just like this. And I apologize, my writing's not the neatest right here, but that's okay. I think you understand the picture. And if you're not sure on that, verify it with a sketch, right? We have -1, -2. Okay, so that vector OC would look something like so. And I could add up all of those components there if I wanted to. Whoops. I could add up all of my components up there, or I could play around and I could say, okay, so 1, 2, 3. I could break it down into its components, and I could verify that absolutely I go over 3 units, because there are 3 horizontal unit vectors here, and I go down 1, 2, 3, 4, 5, 6. So I'm working with 3, -6. Fantastic. I have worked with this algebraically, and I've verified it graphically speaking. So let's take a look at these 3 vectors A, B, and C here. I apologize for in the background you're hearing Sadie munching on her puppy food. But so we have vector A. Vector A reaches out to the point at 2, 1. So that's 2 to the right. That's 1 unit up. Fantastic. A is right here, given with the coordinates 2, 1. I'll label that with a nice A. So vector A, don't forget, vector A comes from the origin and reaches out to that point. Nice and easy. All right, well then, let's take a look at point B. Point B, and we're trying this a second time because I'm trying this a second time because I plotted it in the wrong spot before. 3 units to the left, 4 units up. There we go. We're looking at something like this, -3, 4, and this is point B. All right, if that's point B, then vector B goes from the origin to point B, something like that. Now, if we're trying to come up with the coordinates of vector AB, it's up to us to interpret what they mean by vector AB. Well, vector AB will be the vector going from the point A to the point B. So what I'm looking at right here is something like so. Fantastic. So if I'm looking at that point, then I can look at this in terms of its coordinates. So we'll look at this and we'll call vector AB. We'll assign this the coordinates x, y. So what this really means is if we took vector AB and we set its tail at the origin, 0, 0, then its tip, the arrow tip, would be at the coordinates x, y. Would be at a point given by x, y. Fantastic. But we're not sure which x, y that is because, unfortunately, Mr. Posotka's diagram is not to scale. So we'll algebraically find it here. So we're working here, and we're going to work with x and y separately. X, we'll recall. Okay, well, let's take a look in here, and let's break this down with some vector addition. Because no, I'm not looking to add vector A with vector B here. That would give me something entirely differently, right? If I try to add vector A and B, I set them tip to tail, and I'm trying to find the distance from the origin to that final tip. That's not what I'm trying to do here. So this is really a question of vector subtraction. Because if I write this out with a vector addition statement, then I would be saying here, okay, so I'm looking to try and find the tip to tail that's going on. And I can see the tip to tail that's going on here. It's accomplished through vector A first, so vector A plus vector AB, which is given in pink, plus vector AB. And together, those are equal to vector B. Okay, well, oops, I apologize for that. Okay, if that's the case, I could rearrange this this vector addition statement to come up with really a vector subtraction statement, because what I'm trying to find here, we'll change the view, what I'm trying to find here is vector AB. So all I do is I isolate for that. Okay, so AB is going to be equal to vector B minus vector A. And that's great. Okay, vector B minus vector A. Fantastic. Well, let's take a look a little bit further. If I'm trying to find vector AB, then I'm trying to find how my x-coordinate changes from point A to point B. And I'll say that again. If I'm trying to find vector AB, I'm trying to find how my x-coordinate and later my y-coordinate change as we go from point A to point B. So if I'm doing that, and you might see the connection from here to where we're going next. If we're doing that, let's just look at the x-coordinate. Well, my x-coordinate is going to be equal to how my x-coordinate changes. Okay, so I start with my final x-coordinate, and that's -3, and I subtract because I'm finding the difference. So -3 minus the x-coordinate for A. So I'm working with 2. So -3 minus 2, okay, well, what I'm working with here is an x-coordinate of -5. And then let's try that as well. I've found that I've done that work with my x-coordinate. I need to do that work with my y-coordinate here. So if I'm trying to find the y-coordinate of this pink vector, then I'm trying to find how my y-coordinate changes as I go from point A to point B. So we're trying that out. Okay, so if my y-coordinate is going from point A to point B, then I take my final y-coordinate, which is 4, and it was 4 for point B. And then I subtract my initial y-coordinate, which was 1, so 4 minus 1. So I'm working right here. Okay, I know how to do that. I'm working with 3. So really what I'm finding, I can see here my x-coordinate. I can see here my y-coordinate. if I were to move this, and I'm going to actually copy it because I have that advantage. And again, if I set its tail at the origin, then this point right here, this xy, what I'm working with are these two coordinates that I just found down here. I'm working with -5, +3. -5, +3. Do we think that makes sense given the context of the problem? Given our rough sketch, do we think it's possible that this point is -5, +3? I sure think so. I think it adds up. It makes sense right here. Fantastic work, folks. Now, what we're looking at doing, okay, so let's try and find the magnitude of AB. Well, we can find the magnitude of AB very easily. What I'm working with here, all right, the magnitude of AB, I'm going to, how shall I write it? AB, the magnitude right here, is going to be equal to the square root, right? We're considering this as a right-angled triangle. This is the hypotenuse we're finding. Okay, so the square root of -5 squared plus 3 squared. Nice and easy. All right, so I'm working with the square root of 25 plus 9. I'm working with the square root of 34. Can I break that down any further? No, I cannot. If I wanted to, I could throw it into a calculator. You would not be doing this on an assessment, and we would find that it's a little bit less than 6, probably something like 5.85. This is a rough estimation here. Now, okay, let's kind of break down, though, just to end this off, let's kind of break down how we found those, right? So this -5, 3 point that we found, the coordinates of this AB vector. Well, I found the x coordinate by taking the coordinate of B and subtracting the coordinate of A. So if I'm working here, so if I come up with a rule in general, if I'm working with something like this, if A plus AB is equal to B, and rather if we rearrange that, so AB is equal to B minus A, then I can take this calculation and I can work with my components individually. And I'm hoping you can see that just through the color coding here. The x coordinate, okay, so when I was evaluating the x coordinate of my pink vector, then I was able to look at just the x coordinate of my blue vector and subtract the red vector. And I was able to do that with the y coordinate as well. And then I was able to put them back together to come up with the final point that we're working with. The magnitude, all I'm really doing is I'm taking the difference of these. So I'm taking, okay, so I'm taking the square root, the magnitude, and let's open in that a little bit more. I'm taking my I'm taking x2 minus x1, and I'll color code this. You know what? I'll color code it right now for you folks. I apologize. I think I'm taking a long time. This is a long-winded explanation. That's okay. It'll happen sometimes. So I'm working with x2, which was my B vector, minus x1, and then I square that. And then I add, okay, I'm adding y2 minus y1, and then I square that. And it's the square root of the sum of the squares of the differences. And if you follow that, great. And if not, rewind it, try and follow it. That's what we're working with here to find the magnitude of a vector like this. Now, sure, if you wanted to, you could sit down and try and memorize that. That's not going to be very beneficial to you. It's going to be more beneficial to you to ask yourself, why is this the magnitude of the problem we just found? Well, this is the magnitude of the problem we just found coming from the vector that we created. And we created this vector by coming up with a vector addition statement for the problem at hand. So I think that should give you the necessary skills required here. There is another example, but you know what? I'll encourage you to try those out on your own. The solutions will be posted on the classroom when we get there, but there's no need for a video there. All right, nice work, folks. At this point, you should be able to handle all of the practice problems for section 6.6.